Hello students, today we are going to discuss about phase equilibrium. So first of all we will define the term phase rule. But before that we must know about a heterogeneous system. A heterogeneous system is defined as a system consisting of a number of phases in equilibrium. And the number of phases that can exist together at equilibrium depends upon the conditions of temperature, pressure and concentration of different phases. In 1876, Gibbs gave a generalization known as phase rule, which is applicable to all systems in equilibrium. It is given by a mathematical equation as for a heterogeneous system in equilibrium, F is equal to C minus P plus 2, where F is the number of degrees of freedom, C is the number of components, and P is the number of phases. Now we will define these three terms one by one. So first term is phase. A phase may be defined as any part of a system which is number one, homogeneous and separated from other parts of the system by a distinct or visible boundary. Second, physically or chemically different from other parts of the same system. And third, mechanically separable from other parts of the system. Some examples are number one, ice and water. There we have two phases, one solid and one liquid phase. Second, mixture of gases which do not react. Here we have only one phase, that is gaseous phase. Third example is of two immiscible liquids like water and benzene. There we have two phases, both liquid. And last example is of two miscible liquids. Here we have only one phase. For example, in case of water and alcohol. So next term is components. Components may be defined as a minimum number of independent variables by means of which composition of each phase present can be expressed either directly or in the form of a chemical equation where negative and zero signs being permitted. However, it may be noted that the components of a system may or may not be the same as the actual substances present in the system. This can be explained by examples given below. First example is a water system in which there is equilibrium between ice, water and vapor. Water system is an example of a one component system because the composition of each of the phases can be directly expressed as H2O. Second example is of decomposition of calcium carbonate. Here reaction may be represented as calcium carbonate gives calcium oxide plus carbon dioxide. There are three different constituents forming three different phases, but here the composition of each phase can be expressed in terms of only two of the components or constituents. For example, in case 1, if we take calcium oxide and carbon dioxide, then composition of phase calcium carbonate may be expressed in form of equation calcium oxide plus carbon dioxide, and that of phase calcium oxide can be expressed in the form of equation calcium oxide plus 0 carbon dioxide, and composition of phase carbon dioxide may be expressed in the form of equation 0 calcium carbonate plus CO2. Similarly, in case second, if calcium carbonate and carbon dioxide are taken, and in third case if we take calcium carbonate and calcium oxide, then we can express the concentration of all the three phases by using only two components or two constituents. Hence, it is an example of a two component system. Next, we will give a simple equation by which we can calculate number of components in a chemically reactive system. For this equation is C is equal to S minus E minus R, where C is number of components, S is total number of species or constituents, E is number of equations representing equilibria between the components, and R is number of restrictions for electrical neutrality, and it is applicable only in case of balance, in case of balancing or in case of ions. Some examples are, first example is of dissociation of ammonium chloride in a closed vessel. Here equation may be represented as ammonium chloride gives ammonia gas plus HCl gas. So we will apply this equation and find out the number of components. Here S is equal to 3 because there are three species, ammonium chloride, ammonia and HCl. One equation and one restriction also, because reaction is taking place in a closed vessel, so ammonia and HCl amounts remain same. Substituting these values in equation, we get C is equal to 1. That is, it is an example of a one component system. Second example is of potassium chloride, sodium bromide water system. Here we will discuss two cases. In first case, we will assume that the salts and water does not undergo dissociation. So in this case, we have number of species equal to 5 and 3 already present, that is potassium chloride, sodium bromide and water, and 2 more species, that is sodium chloride and potassium bromide. They are formed by reaction of potassium chloride and sodium bromide. Here we have one equation, that is KCl plus NaBr gives KBr plus NaCl, and R is equal to 0 as we have no ions or no balancing. Thus, by using this equation, we can calculate C is equal to 4. Hence, it is an example of a 4 component system. In case second, if we assume complete dissociation of salt and water, so we have in this case S is equal to 11. First, KCl, it undergo dissociation to give K plus and Cl negative ions. Similarly, NaBr gives Na positive, Br negative ions. Water H2O gives H positive and OH negative, and 2 more species KBr and NaCl. Here we have 5 equations, that is KCl gives K positive plus Cl negative. Similarly, NaBr gives Na positive plus Br negative. NaCl gives Na positive, Cl negative. KBr gives K positive plus Br negative, and water gives H positive and OH negative. Here we have 2 restrictions, that is first for water, that is water is in equilibrium with H positive ions and OH negative ions, and second is for electrical neutrality. Thus, by applying this equation, we have C is equal to 4. Hence, it is an example of a 4 component system. Further, in second case, if we assume complete dissociation and if salts are also taken in equal amounts, then we have one more restriction, that is Na positive should be equal to K positive and Br negative should be equal to Cl negative. So in that case, we will have C is equal to 3. That means system becomes a 3 component. Hence, we conclude that potassium chloride, sodium bromide water system is a 4 component if salts are present in unequal amount, but it becomes a 3 component system if salts are present in equal amounts. Similarly, we take another example of potassium chloride, sodium chloride and water system, and we will discuss both 2 cases, that is in first case when there is no dissociation, and in second case there is complete dissociation of the salts and water system. So we can see here that in both the cases the system is 3 component system. Same as in above case, if salts are present in unequal amount, then the number of components will be 3, but if salts are taken in equal amounts, then the system becomes a 2 component system. Next, we will define the term degrees of freedom or variance. The degrees of freedom or variance of a system is the smallest number of variable factors such as temperature, pressure and concentration of the components, which must be fixed in order to define the state of the system completely. Or alternatively, degrees of freedom may be defined as number of variable factors out of temperature, pressure and composition, which can be varied without disturbing the number of phases present in the equilibrium. For example, consider ice, water, vapor system, that is water system. In this system, there are 3 phases having 1 component. These 3 phases can coexist in equilibrium only at one particular temperature and one particular pressure. Any variation of these factors will lead to destruction of the system. Hence, this system has no degrees of freedom or it is invariant. The same result follows from phase rule equation, that is F is equal to C minus P plus 2. Here we have 1 component system, that is C is equal to 1 and 3 phases, so P is equal to 3. Substituting these values, we get F is equal to 0. Next, we will derive the Gibbs phase rule equation. So for this, consider a heterogeneous system consisting of C components starting from C1, C2, C3 and so on up to Cc, distributed among P phases starting from P1, P2, P3 up to Pp as shown in diagram. As defined earlier, the number of degrees is equal to the number of independent variables which must be fixed to define the system completely. Thus, degrees of freedom is equal to total number of variables of the system minus number of variables defined by the system because of its being in equilibrium. So, to calculate number of degrees, we require two terms, that is total number of variables of the system and number of variables defined by the system because of its being in equilibrium. We will find these one by one. First is total number of variables. Suppose a phase contains two components, then if molar concentration of one component is known, that of other can be calculated. Thus, the phase containing two components can be defined completely by one concentration term. Similarly, if a phase contains three components, then to define it completely, we require two concentration terms. Hence, in general, if a phase contains C components, then it can be defined completely by C minus 1 concentration terms or variable. It is for a one phase. Thus, to define the system completely, that is all P phases, the total number of variables required will be P into C minus 1. Beside these variables, temperature and pressure of the system, which are same, are other two variables. Therefore, total number of variables will be P into C minus 1 plus 2. Second, we will calculate the number of variables defined by the system because of its being in equilibrium. When the system is in equilibrium, the chemical potential, that is mu, is same in all the chemical potential of a component mu is same in all the P phases. Thus, if a system consists of three phases, say A, B and C, then for any component we have mu I A is equal to mu I B is equal to mu I C. These are two equations. Mu I A is equal to mu I B and mu I B is equal to mu I C. That is, for a system of three phases, two equations are known for each component. Similarly, for a system of four phases, we will have three equations, and in general for a system of P phases, we will have P minus 1 equations. Hence, for a system of P phases and C components, the number of equations will be C into P minus 1. This is the number of variables defined by the system itself. This is equal to C into P minus 1. And substituting these values in previous equation, we have F is equal to P into C minus 1 plus 2 minus C into P minus 1. That is, we get F is equal to C minus P plus 2, which is the required equation. Next, we will discuss about phase diagrams. As discussed earlier, the number of phases that can exist together at equilibrium depends upon the conditions of temperature and pressure or conditions of temperature and composition, pressure being constant. These conditions are determined experimentally and then substituted in temperature, pressure or temperature composition diagram. The diagrams thus obtained giving the conditions of equilibrium between various phases of a system are called phase diagrams or equilibrium diagrams. These diagrams contain a number of lines, areas and points of intersection. Next, we will discuss the application of phase rule to one component systems. From phase rule equation, we can see that if there is one component existing in one phase, that is when C is equal to 1 and P is also equal to 1, then the maximum value of F is equal to 2. Hence, all systems of one component can be defined completely by stating two variables, that is temperature and pressure. Further, from phase rule equation, in systems of one component, it will be observed that when the number of phases is reduced to 1, we will have 2 degrees of freedom. Then the systems are known as bivariant systems. And when the number of phases is 2, the system will have 1 degree of freedom and are known as univariant system. And when one component system exists in 3 phases, then system will have no or 0 degree of freedom and is known as non or invariant system. In phase diagram of one component systems, bivariant systems are represented by areas, univariant by lines, and non-variant by a point. We will discuss 2 examples of one component system. One is water system and another is sulfur system. So first we will discuss water system. It is a most common example of one component system, and there are 3 phases: ice, water, and vapor. These 3 phases may occur in 4 possible combinations as follows. First is liquid vapor equilibrium, solid vapor equilibrium, solid liquid, or last is solid liquid and vapor. That is, both 3 phases can exist together. And we know that the number of phases that can exist in equilibrium at any point depends upon the conditions of temperature and pressure. These conditions have been determined experimentally, and a phase diagram is obtained by plotting pressure against temperature. The phase diagram of water, as shown here, consists of number 1, curves. There are 3 stable curves: OA, OB, and OC. And there is a one dotted curve, OA curve. It is a metastable curve. There are 3 areas in the diagram. One to the left of curve BOC, one below curve AOB, and area enclosed by curve AOC. And there is a definite point called triple point. We will define it later, represented by O. So first of all, we will discuss the curves. Look at the curve in diagram. Look at the curve OA in diagram. It represents the equilibrium between water and vapor phase. That is, between liquid water and vapor. That means it is the vapor pressure curve of water. The curve starts from point O, which is the freezing point of water, and ends at point A, which is the critical temperature, beyond which 2 phases merge into each other. Now consider any point on the curve. For a fixed value of temperature, temperature has also a fixed value, or vice versa. Therefore, to define the system completely, we require only one variable, either temperature or pressure. Thus, this system, that is water vapor system, is univariant. The same result follows from phase rule equation. F is equal to C minus P plus 2. C is 1. Number of phases 2. So degrees of freedom will be 1. Thus, this curve is a univariant system. Next, we will discuss curve OB and OC. Look in the diagram. The curve OB gives the equilibrium between vapor phase and ice phase, that is solid phase. So it represents the sublimation curve or vapor pressure curve of ice. The curve starts from point O, that is the freezing point, and ends at B, that is minus 273 degrees Celsius. As in same case above, ice vapor system is univariant. That is, we require only 1 degree of freedom to define the system. Similarly, the curve OC represents the equilibrium between solid phase and liquid phase. Therefore, it is a melting point curve of ice. Similarly, we can see that this is also a univariant system. That is, only has a 1 degree of freedom. Next is curve O dash, which is a metastable curve, and it is a continuation curve of OA. It represents the vapor pressure curve of supercooled water. Why it is a metastable curve? Because on slight disturbance, that is on slight change of conditions, the phase the supercooled phase at once changes to solid ice and curve merges into OB. Next, we will discuss about areas. We will discuss about all the areas. That is, there are three areas in the diagram, one below curve AOB, one below curve AOB, one to the left of curve BOC, and one enclosed by AOC. Look, in all these areas, there is only one phase present. Thus, to locate any point, we require two variables, that is temperature as well as pressure. That means there are 2 degrees of freedom. This result follows from phase rule equation F is equal to C minus P plus 2. Here C1, P1, that is F is equal to 2. So we require two variables to define the system. Thus all areas are bivariant. Next we will discuss the triple point. Look in the diagram. The point O, here all the curves meet each other and there are three phases, that is ice, water and vapor. They are in equilibrium with each other. And from phase rule equation, we get F is equal to 0. That is system has 0 degree of freedom. It means system is non-variant or invariant. And corresponding to point A, there is a particular temperature and pressure. Temperature has value 0.0098 degrees Celsius and pressure has value 4.58 atmosphere. And this point is also known as a triple point or point of intersection. And the main features of they are given below in this table. In all the curves, there are two phases present in equilibrium and these curves are having 1 degree of freedom. Similarly, in areas we see that only a single phase is present and we have 2 degrees of freedom. And at triple point, three phases are in equilibrium, but system is non-variant or invariant. That is, system has 0 degree of freedom. Next, we will discuss the sulfur system. It is an example of a one component system having more than one solid phase. Here we have 4 phases. We know that sulfur exists in 2 crystalline forms, rhombic sulfur and monoclinic sulfur. In addition, we have liquid phase as liquid sulfur and vapor phase as vapor sulfur. So it is an example of a one component system exhibiting polymorphism and solid-solid transformation. The 2 crystalline forms of sulfur are in equilibrium with each other at 95.5 degrees Celsius, which is known as transition temperature. Transition temperature may be defined as a temperature at which a lower temperature stable form of a liquid is transformed into a higher temperature stable form of it without any change in temperature and pressure on the system being 1 atmosphere. And the maximum number of phases that can exist in equilibrium in this system is 3. This result follows from phase rule equation when we take F is equal to 0 and C is equal to 0, because minimum value of F cannot be less than 0 and C cannot be less than 1. So we have maximum number of phases is equal to 3. That means in a one component system, the possibility of maximum number of phases to be in equilibrium is 3. Not more than 3 phases can exist in equilibrium. According to phase rule equation, as discussed earlier, also 4 phases cannot coexist together. This is because on substituting P is equal to 4 and C is equal to 1, we get F is equal to -1. That is, which is meaningless. Hence, for a system of one component, it is not possible to have 4 phases together in equilibrium. However, it is possible to have 3 or lesser number of phases to exist together. The phase diagram of sulfur is obtained experimentally by plotting pressure against temperature, and diagram consists of 6 stable curves as shown in next slide. Curves BO, OA, AE, OC, AC and CF, and 4 metastable curves OD, OG, AD and CD. The curves divide the diagram into 4 areas. Look in the diagram here. We have 6 curves, and these divide the diagram into 4 areas. One below the curve BOAE, one to the left of curve BOCF, one to the right of curve FCAE, and one enclosed by AOC curve. So we will have 4 areas and 6 stable curves. Like in water system, we have discussed all the curves and areas and points of intersection. Here we will be giving just an overview of the different curves, areas and points. Like in water system, here also the curves are univariant, areas are bivariant, and point of intersections, they will be invariant or non-variant. First we will discuss the curves. Here the curve, look at the curve BO. There is equilibrium between vapor phase and rhombic sulfur. So it is a sublimation curve of rhombic sulfur. And 2 phases are in equilibrium, so we can calculate number of degrees of freedom. We will get 1 degree of freedom. Similarly, curve OA gives equilibrium between vapor phase and monoclinic sulfur. So it is a sublimation curve of monoclinic sulfur. It is also a univariant system. Curve AE gives equilibrium between vapor phase and liquid phase. So it is a vapor pressure curve of sulfur. Again, 2 phases are in equilibrium, so we get F is equal to 1. Similarly, we can see for other curves also F is equal to 1. That is, degrees of freedom will be 1. Now we'll discuss the areas. There are 4 areas, and in each area only a single phase can exist. So to define any or to locate any point, we require 2 variables, that is both temperature and pressure. So areas are bivariant. This also follows from phase rule equation. And there are 3 triple points in the diagram: O, point A, and point C. In all these 3 points, there are 3 phases are in equilibrium. So we can calculate number of degrees of freedom from phase rule equation. That comes out to be 0. That is, all the 3 triple points, they are invariant or non-variant. Next, we will discuss the application of phase rule to 2-component system. A 2-component system is the one in which it is possible to express the composition of all phases in terms of 2 substances. From phase rule equation, we can see that a 2-component system can have 3 degrees of freedom. This is because when P is equal to 1, C is 2, so F will be 3. Thus, besides temperature and pressure, we require 1 more variable, and commonly we require concentration to define the system completely. That is, for graphical representation, we require a 3D model. However, in actual practice, a simple diagram with 2 variables is considered and third is kept constant. In this way, we can have following 3 types of diagrams: PT, pressure temperature diagrams; composition pressure diagrams; or temperature composition diagrams. However, in most of the cases, it is convenient to keep pressure constant. Thus, a TC or temperature composition diagram is commonly used. Further, in case of systems having solid and liquid phases, small changes of pressure have very little effect on the systems. Such systems are called condensed system. For such systems, we can write a reduced or condensed phase rule equation as F dash is equal to C minus P plus 1, because 1 degree of freedom, that is pressure, is already excluded. Types of 2-component systems involving solid liquid equilibria. There are 2 types. Type 1, those in which 2 components do not react with each other but simply mix into each other in the molten state or in the solution state. For example, bismuth cadmium system, lead silver system, and KI water system. Type 2, those in which two components react with each other resulting in the formation of a compound. For example, magnesium zinc system. In this system, magnesium and zinc react to form a compound MgZn twice. Or examples, ferric chloride water system or sodium chloride water system, in which components react to form hydrates like Fe2Cl6 into 12H2O or Fe2Cl6 into 7H2O, and in NaCl water we get hydrate NaCl into 2H2. Next we will consider lead silver system. It is an example of a two component system and various possible phases are solid lead, solid silver, solution of lead and silver in molten state, and vapor phase. Since we are considering equilibrium between lead and silver in solid state or in molten state and neglecting, so we can neglect vapor phase. Thus we can use reduced phase rule equation, that is F dash is equal to C minus P plus 1, because we are neglecting effect of pressure. So according to this equation, when F dash is equal to 0, that is minimum value of F dash is 0, then P will be 3. That is the maximum number of phases that can coexist together would be 3. The phase diagram of lead silver is drawn by taking temperature and composition along the axis. Diagram consists of two curves OA and OB intersecting at point O. First we will start with curves. First is curve OA. The curve OA is the freezing point curve of silver to which successive small quantities of lead are added. The curve starts at point A, which is the freezing point of silver, pure silver, that is 961 degree Celsius. It is observed that when we are adding lead into silver, the melting point of silver decreases gradually along the curve AO. At point O, no more lead goes into solution as the solution becomes saturated with respect to lead, and hence the melting point of silver does not fall any longer. Thus, point O represents the lowest possible temperature, that is 303 degrees Celsius, which corresponds to a fixed composition, that is 2.6% silver and 97.4% lead. This point O is called eutectic point, that we will define later. All along this curve, that is along curve OA, there are two phases in equilibrium, solid silver and liquid melt. And here we are neglecting vapor phase. Therefore, from phase rule equation, from reduced phase rule equation, we can see that the system is univariant because C is equal to 2, P is 2, we get F dash is equal to 1. So the curve AO is a represents the univariant system. Next curve is OB. Similar to curve OA, the curve BO is the freezing point of lead to which successive small amounts of silver are being added. The curve starts from point B. It is the freezing point of pure lead and it decreases gradually when we add silver to it. All along this point, two phases are in equilibrium, that is solid lead and liquid melt. Therefore, as before, we have F dash is equal to 1, that is system is invariant. Next is point of intersection O or eutectic point. This is the point where the two curves AO and BO meet each other. At this point, three phases are in equilibrium: solid lead, solid silver and fused mass, that is liquid state, is in equilibrium with each other. Therefore, from reduced phase rule equation, we have F dash is equal to 0. That is, at point O, we have 0 or no degree of freedom. Thus, and also point O represents the lowest possible temperature having value 303 degrees Celsius, below which a liquid phase cannot exist and above which liquid phase cannot be enriched in either component by freezing out the other component. Such a liquid mixture of two components which has the lowest freezing point compared to all other liquid mixtures is called eutectic mixture, and this mixture freezes out completely at a constant temperature, and on freezing gives the two components as in solid phases in the same proportion in which they are present in liquid phase. The temperature corresponding to eutectic point is called eutectic temperature, and it may be noted that this temperature is always lower than the melting point of either of the components constituting the eutectic mixture. Next, we will discuss Pattenson's process for deceleration of lead galena, that is lead sulfide. An ore of lead is generally associated with silver. So when it is worked out for extraction of lead, some traces of silver pass into it because silver is soluble in lead to some extent. The lead thus obtained is known as argentiferous lead, and the deceleration of lead can be easily understood from phase diagram of lead-silver system. The argentiferous lead containing small percentage of silver is first of all heated to a temperature well above the melting point of lead as shown by point X in diagram. It is then allowed to cool along the line represented by dots, that is XY, till point Y is reached. As soon as point Y is attained, lead starts separating and solution will contain respectively increasing amounts of silver. So as soon as lead starts separating, it can be removed with the help of perforated spoons. If we do not remove lead, then the mixture will continue to be richer and richer in silver, and at point A we will get a alloy containing 2.6% of silver and rest lead. So this is all about phase equilibrium. Thank you very much.